b by 2 into b by 2 into sine a by b, and which is equal to 1 by 4 into b into c into sine a. Now the area of triangle ABC is given by 1 by 2 into BC into sine A, and from this we get the maximum area of parallelogram is equal to half of the area of triangle ABC. Now we know the coordinates of ABC, and so the area of triangle ABC is equal to 1 by 2 into determinant, the elements of which are p square minus p1, q square q1, r square minus r1. Now we use the row operations. R3 goes to R3 minus R1 and R2 goes to R2 minus R1, and this determinant reduces to 1 by 2 into p square minus p1, q square minus p square, q plus p 0, r square minus p square minus r plus p 0. And when we solve this, we get the area of parallelogram as equal to 1 by 4 into p plus q into q plus r into p minus r. So let's try to solve one more problem. This appeared in IITJ 1991. A window of perimeter including the base of the arc is in the form of a rectangle surmounted by a semicircle. The semicircular portion is fitted with colored glass, while the rectangular part is fitted with clear glass. The clear glass transmits 3 times as much light per square meter as the colored glass does. Now what is the ratio for the sides of the rectangle so that the window transmits the maximum light? So in this problem we have been given a window is in the form of a rectangle surmounted by a semicircle, and this entire window is fitted with glass. The lower rectangular portion is fitted with clear glass and the upper semicircular is fitted with the colored glass. It has also been given that the clear glass transmits 3 times as much light per square meter as the colored glass does. So we have to calculate the ratio for the sides of rectangle so that the window transmits the maximum light. So how to solve this problem? Let's check out the solution of this. Now this represents the entire window. The lower portion is the rectangular portion and the upper one is the semicircular portion. Clearly the lower portion is fitted with the clear glass and the upper portion is fitted with a colored glass. Now let us say that the length of rectangle is equal to 2x. So this dimension is equal to 2x. Breadth of rectangle is equal to y. This dimension is y. So as we see that this is surmounted on this rectangular portion, therefore the diameter of the circular portion would be equal to the length of the rectangle, and which is equal to 2x. Now the perimeter of window would be 2y plus 4x plus pi x, and let us say that this is equal to p. So the perimeter of window P is equal to 2y plus 4x plus pi x. Now if we say that the rate of light transmission for the colored glass is S, then through the clear glass it would be equal to 3s. Thus if we say that Q is the total amount of light transmitted through this entire window, then Q would be equal to the area of this rectangle into the light transmission rate plus the area of the semicircular portion into the light transmission rate for this portion. So Q would be equal to 2x into y into 3s, because the area of this rectangular portion is 2xy and the light transmission is 3s, plus 1 by 2 into pi x squared, as this is the area of the semicircular portion, into s. S is the rate of light transmission from the colored glass. So this is equal to s by 2 into 12xy plus pi x square. Pi x square is written as it is, plus 2y is equal to p minus pi x minus 4x. So we substitute this value of y over here to get 6x into p minus 4x minus pi x. From this we get q equal to s by 2 into 6 times px minus 24 times x square minus 5px square. So now to find the maximum light transmission, we differentiate q with respect to x to get dq by dx equal to s by 2 into 6p minus 48x minus 10 times pi into x. So for the maximum value of q, dq by dx must be equal to 0. Thus when this equation is equated to 0, we get x equal to 6p divided by 48 plus 10 times pi. Now we have to check whether this represents a maxima or minima, and for that we again differentiate dq by dx with respect to x to get d square q by dx square equal to s by 2 into minus 48 minus 10 pi. Now this is definitely less than 0. Thus d square cube by dx square is less than 0, and so we can say that x equal to 6p by 48 plus 10 pi is the point of maxima. Now we substitute the value of p to get x equal to 6 into 2y plus 4x plus pi x divided by 48 plus 10 pi. Bring this term to this side and get 48x plus 10 times pi x equal to 12y plus 24x plus 6 pi into x. This further reduces to 4 pi into x plus 24x equal to 12y, or pi x plus 6x equal to 3y. We take x as common and get x into 6 plus pi equal to 3y, or 2x by y equal to 6 pi 6 plus pi. Thus 2x is the length of rectangle and y is the breadth of rectangle. Thus the ratio of the length to breadth is equal to 6 by 6 plus pi for the maximum transmission of light through this window. Now students, we have already said about point of inflection, but we don't know what exactly it is. So let's try to throw some more light on point of inflection. So we can say that it is a point on the curve at which the curvature changes sign. The curve changes from being concave upwards, that is the positive curvature, to concave downwards, which is negative curvature, or vice versa. So we can say that point of inflection is nothing but the point at which curvature changes its nature. Either the shift can be from positive curvature to negative curvature, which is concave upwards to concave downwards, or vice versa. At the point of inflection, f dash x is at an extremum, that is maximum or minimum. So we can say that it is a point at which f dash x, that is the slope of the tangent, is at an extremum. Extremum could be a minimum point or the maximum point. So we have seen that the value of the slope changes at different points on the curve. So point of inflection are the points at which f dash x is at an extremum. It could be a maximum or it could be a minimum. Now let's see what is a condition for any point to be an inflection point. The condition is f dash x is at extremum. So if this is at an extremum, then f double dash x must be equal to 0. So this is one condition. But is it the sufficient condition? No. The sufficient condition is the lowest order non-zero derivative must be odd. So f double dash x must be equal to 0. But besides that, the lowest order non-zero derivative must also be odd. So the sign of f dash x on either side of the point x comma y must be the same. If this is positive, the point is a rising point of inflection. If it is negative, the point is a falling point of inflection. So the condition for inflection point is that f dash x should be at an extremum, or f double dash x must be equal to 0. But besides that, the lowest order non-zero derivative must be odd. Also, the sign of f dash x on either side of the point x comma y must be the same. If this is positive, the point is a rising point of inflection. If it is negative, the point is a falling point of inflection. So we say that f double dash x must have opposite signs in the neighborhood of the inflection point. That is, it is changing its nature. So f double dash x tells us the nature of the curve, that is, it is concave upwards or concave downwards. So if f double dash x changes its sign, then it means that the curve is changing its nature, and so either it is moving from concave upwards to concave downwards, or it is moving from concave downwards to concave upwards. Thus the important point is that in the neighborhood of inflection point, f double dash x must have opposite signs. So let's try to see an example. Find the point of inflection for the curve fx equal to x cube. So for this curve, that is x cube, we have to find the point of inflection. So what we do is we draw the curve y equal to x cube. So we see that this is the curve y equal to x cube. So we can clearly see that the curve is changing its nature at the point x equal to 0, or at the origin. It is concave downwards and it is becoming concave upwards. Thus this is a point of inflection. Let's try to see why does this happen. Now we can clearly see that y is equal to x cube. We differentiate it to get dy by dx equal to 3x square. we again differentiate it. So d square y by dx square is equal to 6x. Now we can clearly see that d square y by dx square is 6x. For values of x which are negative, this region, we see that it is negative. D square y by dx square is negative. And for the values of x which are positive, we see that d square y by dx square would be positive. Hence we see that at x equal to 0, we see that d square y by dx square is equal to 0, and hence this is a point of inflection, as d square y by dx square is negative just for the points which are less than 0, and d square y by dx square is positive for points which are just greater than x equal to 0. Thus x equal to 0 is the point of inflection for the curve y equal to x cube. Let's try to solve one more example. Find the point of inflection for the curve fx equal to x to the power of 4. So in this problem we have to find the point of inflection for the curve fx equal to x to the power of 4. Now this is the curve fx equal to x to the power of 4. Now we have to find the point of inflection. So what we do is we differentiate this with respect to x and get 4 times x cube. We again differentiate it to get the value as 12x square. Now this is f double dash x, or the second derivative of fx, and which is equal to 12 times x square. Now if x is equal to 0, we see that f double dash 0 is equal to 0. So this should be a point of inflection, but this is not a point of inflection. Why? Because for values of x which are greater than 0, we get f double dash x as positive, and for the values of x which are less than 0, we get f double dash x also as positive, because this is 12x square. And so we see that on both sides of the point x equal to 0, the nature of curve remains the same. Hence it cannot be a point of inflection, because for the point of inflection we know that the nature of curve must change. Thus x equal to 0 is not a point of inflection. So we can say that this curve does not have any inflection point. So before we start this theorem, which is Rolle's theorem, and this is one of the most important theorems which you would learn in applications of derivative. Just imagine a situation: you come out of your classroom, you sit in your car and you move towards your home. All of a sudden you realize that you have left your bag in the classroom. What would you do? Definitely you are going to turn your car back and go towards your classroom, pick the bag, and once again you'll start proceeding towards your home. So this would be like, let us say that this is your classroom, you start moving and you realize here that you have left and you move back. We have not shown the turning of the car here, but you can still imagine that. So why have we chosen this situation? The entire purpose was that the car was moving and at some instant it had to stop and then again move back and come to the same position. But how it is related to the Rolle's theorem? Let's try to see it. Now Rolle's theorem says that if fx is a real valued function in the closed interval a comma b, such that fx is continuous in the interval a comma